Hello, and welcome to this tutorial on oscilloscope setup for hydrophone measurement. We'll start off by looking at the setup that's normally used when we're making hydrophone measurements. This involves a function generator, often a power amplifier to amplify the signal from the function generator, a transducer, a hydrophone, and finally some form of data acquisition device, often an oscilloscope. It's convenient, both from this tutorial's point of view and in practice, to follow the signal chain from one device to another. We should be able to follow the signal from beginning to end, and this is a useful fault-finding technique. Let's do that now. Signal comes out of the function generator through the amplifier into the transducer, where it propagates through the water, into the hydrophone, and out of the hydrophone into the oscilloscope. There may be other signals that we'd like to consider as well. A synchronization signal from the function generator, and we may wish to monitor the drive signal on the output of the amplifier. This is a useful checklist when we're setting up an oscilloscope or data acquisition device for measurement purposes. Scope impedance, oscilloscope triggering, any trigger delay, the gain on each channel, and also whether or not we're using time domain averaging. In fact, oscilloscope impedance is sufficiently important that there's a PA tutorial dedicated to this topic, so we'll consider that one as having been covered. Now let's look at the issue of triggering. In principle, we could trigger acquisition by setting a level on the acoustic signal that starts our triggering. However, in practice that may not be the most optimum solution. Let's look at that in detail. We begin with an acoustic transducer whose profile is shown in green. We'll be considering measurements at a number of locations in a plane in front of this transducer, and we'll be using the same trigger setup for all acquisition locations, as is common when we make hydrophone scan measurements. Our first position is shown here on axis. It's a nice large signal, and it's relatively easy to determine a level at which acquisition should be triggered. That level is shown here in black, and an acquisition window is shown in orange. This is the point at which signal is acquired. For convenience, I've shown the acquisition window starting at the point at which the trigger threshold is crossed. In practice, we may set a little trigger pre-delay to ensure that we capture the start of the signal. The next trace down is an off-axis position. Because it's further away from the transducer, there's a greater propagation distance. And also, because of that greater propagation distance and spherical spreading, a slightly smaller signal amplitude. Here, with the same trigger level as we previously used, we still have enough signal to trigger acquisition, but if we look at the position of the acoustic signal within the acquisition window, we can see that there's very little difference between that and the on-axis position. We'll now consider a position that's a long way off axis. Here, the distance is increased, and therefore the time delay for the signal to get to the hydrophone is increased further, and similarly, we have a smaller acoustic signal. This time the signal is so small it doesn't even cross the trigger threshold level, and therefore in this location, we'd failed to gain a successful acquisition. The net effect of all of this is that by using a triggering from the acoustic signal, we've ended up turning an apparent profile in green, which is the true profile, to an acquired profile that's in black. If we notice the difference between the lower trace and the middle trace, so the slightly off-axis and on-axis positions arrive at pretty much the same arrival time within the acquisition window. However, the upper signal has failed to trigger at all, and therefore we've got no apparent acquisition. An improvement upon this would be to use a trigger signal that's external to the acoustic signal. Many function generators allow you to output a pulse, which begins and ends when the transducer drive signal begins and ends. Again with our transducer and a hydrophone and our data acquisition system, again an oscilloscope, we can see that the acquired signal now looks something like that shown in blue. We can clearly see there's a small trace at the same time as the transducer drive signal. This is electromagnetic breakthrough. This is entirely common with transducers, and because we're triggering acquisition from the point at which the transducer drive signal occurs, and this signal is travelling through the water at something close to 2 times 10 to the 8 meters a second, it apparently arrives instantaneously. Later on, we have our acoustic signal. And as we scan the hydrophone in a transverse direction across the tank, as it moves out of the main axis of the acoustic transducer, we can see that there's an increasing time delay of the acoustic signal. Furthermore, the signal is getting smaller, as we would expect it to do. Okay, we've now covered triggering. Now let's look at oscilloscope delay. Using the same external trigger signal that we considered previously, and looking in little more detail at that received a hydrophone signal, we can see there's a propagation delay between the start of the synchronization signal and the onset of the acoustic signal. We know there's a relationship between distance, speed, and time, as shown. And using typical values for speed of sound in water of 1480 meters a second and a distance of 30 centimeters, we could calculate an approximate time delay at which to set the oscilloscope. You'll also note here I've approximated the speed of sound in water as 1.5 millimeters per microsecond, which is somewhat more convenient for these calculations than 1480 meters per second. In this case, we can see that we're setting the oscilloscope delay to 200 microseconds. Okay, that's considered delay. Now let's look at channel gain. We'll start off by considering a signal on the oscilloscope that only occupies a small portion of the oscilloscope screen. Here, we've set 500 millivolts per division as our scope sensitivity, and for a 12-bit digitizer, that corresponds to 4096 data levels set across the full scale range. So the maximum positive excursion is 2048. However, because our signal is so small, we can see that it's taking approximately 512 data levels peak to peak, so only about 256 data levels on either side of 0. This means we're only using the bottom 9 bits of the digitizer to digitize this signal. A better situation would be to change the oscilloscope gain to 100 millivolts per division. We'd see a corresponding increase on the on-screen amplitude. We'd now see that the signal is taking more than 3,200 of our data levels to digitize it. We're using most of our 12 bits. We also need to be careful not to set sensitivity too high. Looking at the same signal, but with only 50 millivolts per division, we'd find that the signal would exceed the top and bottom ends of the screen. This is clipping as shown in red. This would result in significant distortion of the waveform on the acquired signal. In practice, therefore, it's better to try and aim for a signal whose amplitude is 75 to 90% of the full scale range. We can now cross channel gain off our checklist. Finally, let's look at averaging. We'll start with a very noisy signal. Here the signal to noise ratio is 0 dB. We have approximately 0.2 volts peak to peak of signal and 0.2 volts peak to peak of noise. However, noise is a random process, and therefore multiple acquisitions averaged together will eventually see that noise interferes destructively, whilst the signal interferes constructively. We can therefore get an improvement in signal-to-noise ratio by increasing the number of averages. Here we can look at 2, 4, 8, 16 averages. So you can see a considerable improvement to signal-to-noise ratio. However, it becomes a law of diminishing returns. To get a reasonably clean signal, we now need 1024 averages. And to be absolutely sure of the signal's amplitude at 0.2 hertz peak to peak with negligible noise, this required more than 20,000 averages. There's also a problem with averaging if we have an unstable trigger. This is often referred to as jitter. Consider here a waveform that's typical for diagnostic ultrasound. We have considerable asymmetry in both the shape and the magnitude of the positive and negative excursions. It's the peak positive that's going to be of most import here. Because of its very short duration, any small shift along the time axis will result in destructive interference. In fact, if we consider 8 acquisitions that are allowed to vary within the range plus or minus 15 nanoseconds, and note here that one major division on the time axis is 200 nanoseconds, we find a really significant reduction in the peak positive excursions. In fact, for the major peak, its amplitude has been reduced by 30% just due to an unstable trigger signal. This can also happen if we have a situation where there's mechanical vibration in the system mounting the hydrophone. And as the hydrophone moves in an axial direction, you can find a small amount of wobble. Therefore, one of the things that's often recommended is, if we've moved a hydrophone in an axial direction, wait a few milliseconds or even a few hundred milliseconds, depending on the inertia of the system, before one starts making acquisition. So, what we've learned in this tutorial is that a stable external trigger signal is critically important. Channel gain should optimize digitisation whilst avoiding clipping. And time domain averaging can significantly improve signal-to-noise ratio, but only if the trigger is stable. We hope you found this interesting. If you did, come back and find some more of the Precision Acoustics tutorial videos.